Okay, so this is English to French translation data set. Here, so this is first is starting is cleaning part. Here, batch size, epochs, latent dimension, that is a number of neurons. We want to set number of samples, data path, part 2 data set. Then we have cleaning part. So here we are splitting, reading each and every sentence, basically line by line, splitting it into characters and generating vocabulary for input as well as for target. So for input, we are calculating the number of how many samples. We are calculating unique input tokens, unique output token, that is our vocabulary size, that is number of characters. And maximum sequence length. So for input sentences, maximum sequence length is 15, and for output sentences, that is for target sentences, we have output sequence length is 59. So this is in terms of characters, number of characters. So in this data set, they have what they have done is for all the sentences, you can take. Suppose one sentence is of 5 characters, second sentence is of 6, third sentence is of 7 characters. So they have taken the maximum length sentence as input for encoding. So one hot encoding is used, and similarly for output, they have taken the maximum length sentence for encoding. Now, one thing that you also can do is you can, instead of taking the sentence that is having maximum length, number of characters with the maximum length, you can also take some intermediate value. For example, you have sentences for, let's say, uh, 4 characters, 6 characters, 7 characters. So on an average, suppose you have most of the sentences were 7 characters. So and one sentence was 20 characters. So you can also trim this one and you can take the maximum length as 7 instead of taking it as 20. So what they have done is they have taken the maximum length sentence as the for encoding your input. Okay, similar thing goes for your output sentence. So this is the pre-processing part. Similarly, you can, so these are the characters and indexing for each and every character. So total 93 characters in output. Then, okay, so this is now let's come to encoder decoder part. So in encoder, they are, first of all, we are generating 3 dimension vector. So first dimension is number of sentences, number of input text that we want to translate. Second dimension is maximum length of each and every sentence, because we want to one hot encode it. And third is number of encoder tokens. So okay, I will explain this one. So basically this is vocabulary size for the input, and similarly vocabulary size for the output. Okay, now decoder, here we have two types. In decoder we have input data plus we take data from the output. So if we have a look at the general Seq2seq model, we have input sentence. Okay, so this is our encoder part. It generates something, and then we have decoder part. So while training, decoder takes input from the decoder as well as it takes input from the encoder. And this is also LSTM, and this is also LSTM. Two LSTM layers are there. So this is this first LSTM layer is working as encoder, second LSTM layer will work as decoder, and output for these are discarded. We don't want output in these layers, we only want output in the last cell that it is generating. What actually we want is we want hidden state and cell state for each and every basically we can say uh, input, basically as neuron. Okay, so for each and every neuron we want only hidden state, cell state. Basically we want intermediate representation, whatever it is generating, as encoded output from the input layer, right? And similar goes for output. So here we will pass hidden states and cell state of encoder. So in generating the first value over here, so we require input from encoder, we require inputs from decoder as well, because we want to train on decoder input as well. And two things, and third, we want target whatever we want as output in the decoder. So three things are there. So and this input data and target data, this is its dimension is described as, for example, I had data set of suppose so 5 characters, 1, 2, 3, 4, 5. Second, we have 6 characters. So for giving, if I'm giving first input sentence as first training example x1 as my input to this encoder part, so what I will give is I will give a feature vector, and this feature vector is of size vocabulary, which is in our case is I think 15 for input and 93 for output. Yes. So the size of first would be 15, and if first word is A, so wherever A is present, this would be 0, rest all would be 1. Sorry, if A, whenever A is there, that is 1, rest all would be 0. So this is one hot encoded and its value is 15. So basically feature set size is 15 for each and every word that we want to character that we want to give as input to the layer. So this is 15. For second character it would be again be 15. So 0 0 0 1 0 0 0. So size of this would be 15. So this is the first character, second character. This whole combines of first sentence, one sentence. So that is why it is 3 dimensions. So first dimension is number of sentences, second dimension is the length of number of characters in that sentence, and third dimension is defines the one hot encoded output for each and every character that we are having in that sentence. Okay, so that is why it is 3 dimension. Now so that is why, so we are filling this zeros 3 dimension array that we have generated, and we are filling it whenever that word is present. So in encoder we are uh, setting 1 wherever that encoded wherever that word character is present, and we are setting zeros because zeros was already there. So this is one hot encoding simply in 3 dimension. Okay, for encoder as well as for decoder. Now let's have a look at basically encoder and decoder training part. So in encoder inputs, so what we will give as none, because we are not giving data set yet, and we will give number of encoder tokens. Now okay, so this is uh, we are creating one LSTM layer, and one LSTM layer having 256 neurons, and return state is true because we want hidden states, previous hidden states, hidden and cell states. So return state is true, and this is only one LSTM layer, basically encoder part. Okay, and input is input shape. Okay, input shape, if I have the model summary over here, if I print model summary, so this is input shape, so this is vocabulary size, this is encoder part. So in encoder this is vocabulary size because each and every vector, or you can say feature size, features, number of features are 71. So that is your, and none is, this is a number of training examples and your each and every sentence. Okay, so for each and every sentence you are generating the encoded input. Okay, this is encoded output, hidden state, and cell state. Three things whenever we are creating a LSTM layer, or maybe encoder, maybe a decoder. Encoder is also a LSTM layer, decoder is also a LSTM layer. So whenever we are creating this, it returns three things: hidden state, cell state. Hidden state is nothing, that is the output. Cell state is memory, And encoder output, we don't want encoder output, so we will discard it, because in input we don't want encoder outputs at each and every cell. We don't want it. We want hidden and cell states only. So those hidden and cell state will be passed to decoder. Okay, so we will discard, so we only keep hidden state and cell state, and we discard the encoder output. And now we will pass this in the decoder. Now before passing, let's see the inputs for the decoder. So again, same thing, number of decoder tokens, and this is input for decoder. So here decoder is again LSTM layer, nothing, it's just nothing, where we are defining number of neurons and we are defining the input shape. So input shape is here. Okay, so decoder outputs, again hidden state and cell state, because we want, whenever we are training this LSTM, so for this LSTM we want its own outputs, hidden state and cell state, to pass into whenever we are training it again and again. So we want its own hidden and cell states as well, plus we want hidden and cell states from encoder as well. Okay, so here decoder LSTM, we have defined inputs already, and we will initialize it with the encoder state. So initial state, in the encoder, initial state was some random value, and in decoder, initial state would be the encoder states. Okay, and then finally we are applying dense layer over here, because we want output, so we will apply a dense layer. So this is a dense layer, and because we want probability values, so this is softmax would be used in this dense layer. So this is dense layer after decoder LSTM. Okay, so softmax function is used because we are generating probabilities. Okay, so it will basically give me some vector of probability. So it will give me 0 0.1, 0 0.2, 0 0.9, and so on, up to maybe 93 rows. And I will select this one, and I will say, okay, it is generating some word which is at this position, maybe A. Okay, so we use maximum value, that is maximum probability, to decide which character it is generating. Then Keras again, so we are building the model, creating the model, compiling it, optimizer, categorical cross entropy, because softmax we have used, accuracy, and we are fitting the model. So we have input, decoder output, basically target that we want to train upon. So we have, because in decoder we have input as well as we have output, while in encoder we only had input. Then batch size epochs, these we have previously defined. Then we are splitting the data set into 20% and 80%. So 20% is validation data set. Now while fitting this model, we are saving this model as sequence to sequence, because only training is done. Training part is completed. And after this, we want to test it for the for each and every output. Now, while testing, one thing we need to make sure of is, suppose I had this data set and this is encoder, and uh, then we have decoder. So in decoder, if I'm passing first, so because it is trained, already trained, so it will have some values, H and C values, and this will also have some H and C values. Okay, so each and every cell would be having some values. Now, if I'm passing, so for testing, at the testing time, what I want is it should give me it should give some it should take some input as sequence of characters. Let's say hello, how are you? So hello, let's say. So this is sequence of character it should give, and it should give me the translated output. And for translated output, so one thing that we will do is, so we will pass start symbol as input. Here we are using tab space as start symbol because my data set looks something like this. So this is input sentence, then a tab space is there, and then a translated sentence. So input sentence, tab space, and translated sentence. So for so while pre-processing the data set, what we had done was translated sentence was added with the start token. Start token is nothing, we have added with the tab space. So this was, if this was the input sentence and this was the target sentence, so we have added a tab space over here and we say that this is the start symbol. Okay, so for predicting the first output, we require the input from the encoder. From here we require input from the this from here from the previous hidden and cell states of the decoder itself, H and C. I will write it like this. Plus we require the start symbol. Three things are required to predict the first value, that is translated value. Suppose after translating it is generating F. So this is again passed to uh, second neuron. Okay. So same thing is written in the code itself. So now model S2S I have saved with the name. Uh, I have saved this encoder decoder model with the named sequence to sequence S2S, and I will reload it now because it was trained already. I will reload it and mm, reload it and use it for prediction, for testing part. Now, before that, if you have a look at the summary of the model, so this is first your encoding input for the encoder, and this is input for the decoder. This is your first LSTM layer. It will take input from the input 1 layer, that is from encoder part, and this is your second LSTM layer. It will take input from the second uh, second input, that is your decoder part, decoder translated output, translated target that you want. So this is your target, this is your input. Okay, these two things are there, plus it is also connected to both the LSTM layers. Both, which one? So first layer is the encoder layer, that is coming encoded inputs that are coming from the encoder, this layer input 1, this first, sorry, this LSTM layer 1, and this is second LSTM layer, that is itself. So two LSTM. So this decoder, if you have a look at, is connected to three things. First is its own target output that it wants. Secondly, the input from the LSTM layer, output from the LSTM layer, that is encoder, and the output from the decoder itself. So whatever it is generating itself. So three things it is connected to. Okay, then we have a dense layer. So dense layer is only connected to the decoder, that is LSTM1. So it is only connected to LSTM1. So this is the model that is trained, already trained. Now we will reload the model, so that we have trained already, having hidden states and cell states. So we are reloading it for prediction. Now we want to do prediction. Okay, so we are reloading that model and we are again defining the encoder model. It should consist of encoder inputs, that is your model input 0, that is your again the same input, this one, plus the encoder states, and those states are having hidden states and cell state, not the output state. Only these two things are there. So we define encoder model. Similarly, we define decoder model. So in decoder model, if you have a look at this over here, so decoder model consists of decoder inputs, decoder state inputs, decoder output, and decoder states. So everything is defined. So decoder states is its own cell state and hidden state. Then decoder outputs is hidden. Decoder output is whatever it is generating after training the LSTM layer, its own, after whatever it is training the LSTM layer itself. So it is generating something as output. So that thing plus decoder states input plus decoder input. So that is your model input 1. So basically your target, what you want to generate. Okay, so four things. This is how decoder model is created. So this is encoder model, this is decoder model. Decoder model may you have to make sure three things basically are there. First is your input that is coming from the encoder part. Second is its own training values, that hidden and cell state. And third is whatever target it is generating. it wants as output, that is your translated output. And fourth thing also is there, that is your first start symbol. Now one more thing is there. So because at time step t is equals to 1, it is generating the second character, because this is the first character, second character is this one. So at t equal to 1, so that is why it is shifted 1 to the right. Okay, so this thing also you need to remember while prediction. So at time, or you can say at time t is equals to 2, it is predicting the first character like this. Mm. Or sorry, at time t is equals to 1, it is predicting the second character, because at time t is equals to 1, we are just passing the first character. We are not training the first character. First character, that was our output, our target output. Okay. So now this reverse lookup is nothing. It's just because it will give me some array, that is 0 0.1, 0 0.2, 0 0.5. So reverse lookup is I will select this one and I will go to my dictionary where I had stored A, B, C, D characters and 0. Okay, I'm saying this is so A, B, C, D, and I have stored index. So I will go to index wherever the C was present, and I will say, okay, this character is C. So reverse lookup is just converting probability values again to the character. So reverse lookup is there, then compiling and fitting the model. Uh, okay, after fitting this, so this is the code sequence, this is function. So what it is doing is, okay, let's have a look at. So here seek, I am generating, I want to predict for 50 sentences, let's say, suppose. So I can predict for 20 also, for 50, for few sentences. So first sentence I'm taking, and first sentence is basically inputs, first input sequence maybe weight. So this is my first input sequence, and I'm passing it to function decode sequence. Now decode sequence, what it is doing is, it will take this input, first only one sentence that for which I want to translate. So I want to translate, let's say, wait, or maybe some other some other sentence, maybe run. So I will, so my input sequence is run, and I will call this function decode sequence, and this decode sequence will, what it will do is, it will call decoder model for prediction. Okay, so it will call that decoder model that we have generated for prediction. Now one more thing, so you need to again check pre-process it, because you need to populate the first character. So you need to start with the second prediction of the second character instead of the prediction of the first character, and your first character you need to append that \t. So for all the sentences, first of all, you need to append start symbol, also the ending sequence, ending symbol while pre-processing. That is one thing. And you need to generate second symbol using the first sequence at time t is equals to 1, at time step t is equals to 1. So shifting process is there. Okay. So it is doing nothing. So this function is doing nothing. It's just calling that decoder that you have generated, calling it and finding it. It will give you some values, and you will select the maximum probability values out of the vector that it is generating, and you will reverse look up and search which character it is generating and print it. So that is the only thing. So, and combining all the whole sentence into the decoded sentence and print it. So this is how machine translation will work. So the only thing that is complex in this whole is how you define the encoder and decoder states. So you need to be very careful while uh, setting these parameters. Okay, so this was it.
I've
I've
submitted it. I
submitted
think
it. I think
the
the
code was
code
more or
was
less
more or less
similar.
similar. Okay. You have submitted it, so that's good.
Yes, ma'am.